Dear students, welcome to the EPG Pathshala. I am Dr. Gurmeet Singh, working as a professor of chemistry in the University of Delhi. Today, we are going to discuss about the module Magnetic Force Microscopy. We will deal with the introduction part in this particular presentation. This comes under the presentation and under the paper called Surface Analytical Techniques Part 1. When you finish studying this module, you will be able to understand the basic concepts concerned with this, overview of this, and advantages and disadvantages of this particular technique. When we come down to the basic concept, we will know that the magnetization behavior of a ferromagnetic material is governed by the characteristics of the magnetic domains and their dynamics. Magnetic domain imaging provides the most direct access to the effective magnetic properties from macro to nano scale for fundamental and application point of view. Various studies have been performed to directly visualize the magnetic domains and their dynamics in different materials using techniques such as magneto-optical curve microscope called MOC, Lorentz electron microscope, scanning electron microscope with polarization analysis, neutron grating interferometry technique, and magnetic force microscopy. Out of the above techniques, which I have enlisted, MF has been extensively used in the past 2 decades for depiction of magnetic microstructures at the surface of ferromagnetic substances at micro or nanoscale for that matter. MFF can image concurrently the magnetic stray field of the surface and topography with the resolution of about a few tens of nanometers. The long-range magnetic dealings for less sensitive to topographic irregularities of the sample can also be studied with this MF microscopy.
Almost every surface property measured by AFM is acquired by the process depicted. MFM measurement in the axis series AFM follow the same procedure. For MFM, the surface properties would be magnetic properties and the interaction force will be the magnetic force between the magnetized tip and magnetic sample. However, in addition to the magnetic forces, van der Waals forces always exist between the tip and the sample. These van der Waals forces vary according to the tip sample distance and therefore are used to measure the surface topography. MFM images the spatial variation of magnetic force on a sample surface with the MFM tip coated with the ferromagnetic thin film. In the axis series, AFM surface topography is obtained in true non-contact mode. At the same time, the MFM image is generated by measuring either the amplitude or the phase change of the cantilever oscillation from the magnetic force between the surface and magnetized MFM cantilever. MFM images contain information on magnetic domain distributions on the sample surface. MFM can be used to image naturally occurring and deliberately written domain structures in magnetic materials. During the MFM measurements, there are 2 forces acting on the tip, magnetic and van der Waals forces. Hence, in FMM, the signal contains both information of surface topography called topo signal and surface magnetic property called MFM signal. generated by van der Waals and magnetic forces, respectively. The dominating force depends on the distance between the tip and the sample surface because the interatomic magnetic force persists for greater tip to sample separation than the van der Waals forces. These van der Waals forces vary according to the tip sample distance, therefore are used to measure the surface topography. If the tip is close to the surface in the region where standard non-contact AFM is opened, the image will be predominantly topographic. As you increase the separation between the tip and the sample, magnetic effects become apparent. Collecting a series of images at different tip heights is one way to separate magnetic from topographic effect.
We have been talking about magnetic force microscopy, and here a brief outline of that has been given. It is abbreviated as MFM. Non-contact scanning probe microscopy is referred to as SPM. Close relative of atomic force microscopy AFM, and force sensing probe, which is magnetic, is also indicated here. This was developed in 1987 by Y. Martin and H.K. Vikramasinghe. Magnetic imaging of force microscopy with 1000 angstrom resolution. This was a paper published in Applied Physics Letters in 1987. And here in this slide, AFM and MMF. AFM on the left, MMF, which is magnetic force microscopy, on the right. These images have been given here. These are the images of glass ceramics, which has been indicated here. It talks about a method which is known as bitter method, decoration method, image of magnetite or magnetic interaction between small supermagnetic particles. It is known as ferrofluid, and magnetic stray fields from sample surfaces are analyzed. This has been indicated in the diagram, and wet bitter method picture that one gets of magnetite has also been shown here. Dried bitter method TM60 also been shown in the figure. Can we improve over this bitter method, about which we had talked about in the last slide? Yes, we can, with the help of control the force principle. Scanning force microscopy, if we use and measure and manipulate the surface and magnetic forces, can really help in getting better images. Here, cantilever and sharp tip have been shown. Magnetic force microscopy, here it produces a 2D image of the derivatives of the stray magnetic fields, that is, we call magnetic forces, from a sample with lateral resolution of 50 to 100 nanometers. In the diagram here, a sample has been shown and its surface has been indicated. The surface forces, which vary from different quantities, have been given. Surface forces long range from 10 nanometers to 100 nanometers, magnetostatic and electrostatic forces. Then we have nanoscale 10 nanometers or van der Waals or Coulombic forces, which can play its role. These are all surface forces. And finally, on atomic scale, we can have ionic forces or chemical absorption forces. The sample also has been indicated here. Comparison of AFM and NMF. MMF and AFM, when we compare, we get this kind of flow diagram. In short range forces, up to about 10 nanometers can be indicated this way through contact mode. Sharp tip interacts with surface forces, maps surface topography, and for the other kind, non-contact mode, where we get MFM images, magnetic tip interacts with sample stray magnetic field. It maps the magnetic forces MFM and AFM with magnetized tip have been given SPM component. SPM controller electronic component is there, which gives the feedback control contact loop. Then controller electronics sends this to deflection sensor. And on this side, right side, we have shown SPM consists of 5 key components. These are sharp tip probe, XYZ scanner, deflection sensor, feedback control loop, and probe oscillator. Piezoelectric biomorph. We have given the images of these instruments. A real MFM has been shown. The monitor has been shown, through which interaction between various layers can be talked of. Then we have scanner head here, sample holder is there, cantilever head holder is there, XYZ recorder is there, and we can record this with the help of these units. This is called digital instruments nanoscope, which has been shown here. We have given the advantages and disadvantages of the MF. Deflection sensors have been shown. Several different methods are there. Most widely used is the beam deflection technique. Here, laser sends the rays to mirror, and that gets deflected onto the sample, and which analyzes this and goes to a potential photosensitive detector, and that is analyzed depending upon the reflections which are sent through the beam deflector. As the cantilever bends, the positive side or the position of the laser beam on the detector shifts. Long beam path amplifies deflection, can detect cantilever deflection which are even less than 0.1 nanometers. Video imaging of these cantilever reflection tips can be seen on the television screen or on the monitor screen. The magnetic force microscopy is a variety of atomic force microscope where a sharp magnetized tip scans a magnetic sample. The tip sample magnetic interactions are detected and used to reconstruct the magnetic structure of the sample surface. Many kinds of magnetic interactions are measured by MFM, including magnetic dipole-dipole interactions. MFM scanning often uses non-contact AFM, abbreviated as NCAFM mode. Magnetic force microscopy. This gives a mathematical relationship and has been shown that what way the tip scans the surface and these forces are measured. MFM is based on the use of a ferromagnetic tip as a local field sensor. Magnetic interaction between the tip and the surface results in a force acting on the tip, which can be detected from the deflection of the cantilever. Alternatively, the dynamic properties of the tip oscillations, that is amplitude, phase, or frequency, can be used. In this case, the observed signal is proportional to the derivative of the force. The tip is scanned several tens of or hundreds of nanometers above the sample, avoiding contact. Magnetic field gradient exerts a force on the tip's magnetic moment, and monitoring the tip or cantilever response gives a magnetic force image. To enhance sensitivity, most MF instruments oscillate the cantilever near the resonant frequency with a piezoelectric element. Gradients in the magnetic forces on the tip shift the resonant frequency of the cantilever. Monitoring the shift or related changes in oscillation amplitude or phase produces a magnetic force image. Applications of this are magnetic recording media, micromagnetism, domain well dynamics and pinning, failure analysis in electrical circuits, studies of superconducting current, etc. can all be analyzed with the help of MFM spectroscopy or microscopy as we call it. Magnetic force microscopy images the spatial variation of magnetic forces on the sample surface. Resolution is 10 to 25 nanometers. The system operates in non-contact mode. An image taken with a magnetic tip contains information about both the topography and the magnetic properties of the surface. Which effects dominate depend upon the distance of the tip from the surface. Because the interatomic magnetic force persists for greater tip to sample separation than the van der Waals forces. If the tip is close to the surface, in the region where standard non-contact AFM is operated, the image will predominantly be showing topographic part of the surface. As the separation between the tip and the sample increases, magnetic effects become apparent. A magnetizer is needed to magnetize the tip. Note that the structure of soil magnetic samples like permalloy or garnet films can be significantly changed by the field of the tip that has relatively high coercitivity. Tip-coated or tip-induced reorientation of the surface magnetization and surface-induced reorientation of the tip magnetization can complicate the image interpretation. This gives the lift mode of MFM and EFM. Since magnetic forces, or electrostatic as we call it, can be either attractive or repulsive, problems with the feedback loop stability in the non-contact imaging mode are likely to occur. This has been shown in the diagram here. Cantilever measures surface topography on the first scan. Cantilever tends to lift scan height. Cantilever follows stored surface topography at the lift height above sample while responding to magnetic, that is electrical influences on second scan measured by amplitude, phase and frequency detection. Magnetic force microscopy, as stated earlier, has special probes used for MFM. There are magnetically sensitized by sputter coating with a ferromagnetic material. The cantilever is oscillated near its resonant frequency, that is about 100 kilohertz. The tip is oscillated tens to hundreds of nanometer above the surface. Gradients in the magnetic forces on the tip shifts the resonant frequency of the cantilever, and then we monitor this shift or related changes in oscillation amplitude or phase produces a magnetic force image. Many applications for data storage technology are there while using MFM. The mechanism or mechanistics of this instrument's components. The main elements of an MFM system are piezoelectric scanning part. This moves the sample in an X, Y, and Z direction. Voltage is applied to divide electrodes for different directions. Typically, a 1 volt potential results in 1 to 10 nanometer displacement. Image is put together by slowly scanning sample surface in a faster raster fashion. Scan area range from a few to 200 micrograms or micrometers. Imaging time ranges from a few minutes to 30 minutes. Restoring force constant on the cantilever range from 0.1 to 100 nanometers based on the substance of the cantilever. Magnetized tip at the end at a flexible lever, that is cantilever, which we use. Generally an AFM probe with a magnetic coating is preferred for want of saving the tips. So we have the diagram given here. Then we come to the overview of this. In magnetic force microscopy, when we start measuring, it involves the magnetic force between the sample and the tip, and it can be expressed by a mathematical relation which has been given below. Here, M is the magnetic moment of the tip, approximated as a point dipole. H is the magnetic stray field from the sample surface, and mu0 is the magnetic permeability of the free space. Because the stray magnetic field from the sample can affect the magnetic state of the tip and vice versa, the interpretation of MF measurement is not straightforward. Requirements for MFM tips. The cantilever tip assembly is the critical element of a magnetic force microscope. Unlike in scanning tunneling microscopy, where and the repulsive mode AFM, the tip shape is given in a site called www.intechchopin.com. Magnetic force microscopy will involve basic principles and applications, and 45 important because of the long range nature of magnetic forces. You will find there are 45 techniques where it can be used. MFM can be used to image several magnetic structures, which includes domain walls, block and anneal, closure domains, recorded magnetic bits, etc. Moreover, motion of domain wall can also be studied in an external magnetic field. MFM images of various substances can be seen in the following books and journals which have been published regularly. One is thin film nanoparticles, nanowires, permalloy discs, and recording medias. The advantages of this MFM originates from several reasons, which include the sample does not need to be electrically conductive, which is a major advantage. Measurements can be performed at ambient temperatures, and it has to be in ultra high vacuum called UHV, in liquid environments also, and at different temperatures as well, and of course in the presence of variable external magnetic fields. Measurement is non-destructive to the crystal lattice or structure. This is a very big advantage when we compare it with the other techniques. For example, if you use ESCA, which we call it as XPS, there the sample is destroyed. So in this technique, the sample is not destroyed, and we can carry out the measurements once again. Therefore, this is a non-destructive technique to the crystal lattice or structure. Long-range magnetic interactions are not sensitive to surface contamination. Therefore, one can study that also. No special surface preparation or coating is required, as we have in the case of a large number of electrochemical techniques, where the surface preparation plays a very important role. Deposition of thin non-magnetic layers on the sample does not alter the results. Detectable magnetic field intensity, H, is in this range of 10 amperes per meter, detectable magnetic field B is in the range of 0.1 Gauss, that is 10 measured forces are as low as 10 to the power minus 14 N with a special resolution as low as 20 nm. MF can be combined with other scanning methods like SCM if required. There are many disadvantages when we use this technique. There are some shortcomings or limitations or difficulties when working with an AF with magnetic force microscopy, such as the recording image depends upon the type of the tip and magnetic coating which has been done due to the tip sample interactions. Magnetic field of the tip and sample can change each other's magnetization, which can result in nonlinear interactions. Continuing with the disadvantages, this hinders the image interpretation. Relatively short lateral scanning range, order of hundreds of micrometers. Scanning, that is lift height, affects the image. Housing of the MFM system is important to shield electrogenesis noise. It is also able to shield electromagnetic noise, that is Faraday cage is the one where this is carried out. Then acoustic noise entry vibration table one can use to avoid the acoustic noise. Then airflow, air isolation can be done and airflow can be given. And static charge on the sample is the one which also provides difficulties. Schematic diagram of magnetic force microscopy. It shows what way the glass hard disk samples look like. A graph has been given where ferromagnetic tip, non-contact mode, DW force short range forces, magnetic force long range force measurement, close imaging, that is what way the topography moves. All these can be measured with the help of this. These are some of the figures that one obtains by using magnetic force microscopy. So first is with the image of photo taken by nanoscope SPM, courtesy data imaging, see this. Then we have overwritten tracks on a textured hard disk which are 25 micron scan. So students, having learnt about magnetic force microscopy from the point of view of introduction and instrumentation, one can now summarize what exactly we have learned in this particular module. MFM is a relatively new technique for imaging magnetization patterns with high resolution and minimal sample preparation. The technique is an offspring of AFM. That means it is similar to what we use for AFM. It's a sister technique to AFM, we can say. That's why sometimes we put it that this technique is an offspring of AFM and employs a sharp magnetic tip attached to the flexible cantilever, as we find in the AFM technique also. The tip is placed close to the sample surface from some nanometers to few micrometers and interacts with the stray field emanating from the sample. The image is formed by scanning the tip laterally with respect to the sample and measuring the force or force gradient as a function of position. The interaction strength is then determined by monitoring the motion of the cantilever using a sensor. Although a lot of effort has been done in order to get quantitative information, magnetic force microscopy is still predominantly a qualitative characterization technique. I am sure you would have understood the importance of this MFM technique when we carry out the analysis of the surfaces. Thank you very much, please.